masagot ang malnutrition?
Pangarap ko pong magkaroon ng effective communication means for emergency.
Pangarap kong ma-maximize yung renewable energy source and to reduce the carbon dioxide emission.
Recording in progress.
Pangarap ko pong maging scientist.
Ngayon na o simulan na, humanda sabay-sabay akyat. Hawak kamay tayo'y angat, lipad. Ating nabutin ang pangarap ni Juan sa pamamagitan ng agham. Ang kaunlaran ay makakamtan kung lahat magtutulungan. Tara na, sama-sama itaguyod ang siyensya. Maayos na bukas para sa Pilipinas. Ating nabutin ang pangarap ni Juan sa pamamagitan ng agham. Ang kaunlaran ay makakamtan kung lahat magtutulungan. Tara na, sama-sama itaguyod ang siyensya. Maayos na bukas para sa Pilipinas. Maayos na bukas para sa Pilipinas. Maayos na bukas ating iparanas sa bayang Pilipinas.
We are now living in a new normal. This COVID-19 pandemic marks as one of the global challenges experienced in this generation. It forces every sector of our society to innovate in order to move forward. We, at the Industrial Technology Development Institute of the Department of Science and Technology, is trying every possible ways to continue our service to our people, without compromising the safety of each and everyone.
recognizing the critical role of science and technology in economic development and progress. The Balik Scientist Act, or Republic Act 11035, was signed into law last June 2018 by President Rodrigo Roa Duterte.
This is actually putting into law a program that has been started by the Department of Science and Technology almost 40 years ago. But we need some legal support so that we can implement it in a better way. The Balik scientists will have an easier time in terms of coming here to the Philippines and rendering services.
Who is the Balik Scientist?
Experience and expertise of Filipinos who have made good practice of being scientists abroad, so that they can share whatever they have in terms of knowledge and wisdom to our own institutions, our own researchers.
My role and responsibility of a Balik scientist is to be not just a teacher or a facilitator, but also a pusher of innovations within the program.
Balik scientists are given support by the government for their stay in the country and are likewise provided with a wide array of benefits to ensure their maximum output.
The best incentives or privileges or benefits are having to be exposed with our farmers.
My greatest privilege would be doing collaborative work with fellow Filipinos.
The DOST, as the leading agency in charge of the Balik Scientist program, is tasked to facilitate the placement of the Balik Scientist among its priority areas from its sub-agencies. P-Card, PCHRD, P-Shared, Partnering with the DOST are the host institutions, private or public entities, providing the appropriate resources to the Balik scientist in the completion of their research activities and other tasks.
I think the role of the institution is to give the space or the laboratory needed for the program or the project.
Working together, the DOST, the Balik scientists, and the host institutions have proven the importance of collaboration and cooperation, critical of any nation's vision for success.
I am an advocate of Balik Scientist program. Kay being one, I really truly felt that Balik Scientists would be able to help in uplifting the economic growth of the country.
My hopes is to really contribute to the space agency. It's very, very pragmatic, and we will need everybody's help, and also promulgate the STEM program here in the Philippines.
We really need to encourage other Balik scientists or other scientists abroad to give their time. They need to give back and help the country.
With the enactment of the Balik Scientist Act, the country is looking towards a stronger and more solid science and technology foundation, propelling the nation to further heights. Change has come indeed for science and technology. Science for change. Science for the people.
Magandang araw! Welcome to the fourth installment of our Virology and Vaccine Institute of the Philippines or VIP program webinar series. I am Bernard Jude Gutierrez from the Environment and Biotechnology Division of the DOST ITDI, and I will be your host for today. This 2-day webinar is part of the Virology and Vaccine Institute of the Philippines, or VIP's information and education campaign on virology and other related topics. This learning session is made possible by the collaborative efforts of the DOST Central Office, DOST ITDI, DOST PCHRD, DOST PCARD, and the DOST Balik Scientist program. Let's check first the number of participants here in our Zoom meeting room, as well as our audiences from our Facebook and YouTube live streams. So here in Zoom, we have 248 participants. Here on YouTube, we have 9 watching. And here on Facebook, we have 32 people watching. So just a reminder for our Zoom participants, kindly rename your Zoom account into this format: affiliation_full name. Also, don't forget to mute your microphones, and please do not forget to answer our training evaluation form at the end of the lecture to secure your certificates and a copy of our speaker's presentation. So before we start with our second session, thumbs up react naman po dyan sa mga participants na kasama natin kahapon. So may mga ano ba kahapon? I see some thumbs up. Ayan, meron mga nag-thumbs up. So pumunta kayo nung kahapon. For this second day webinar, we shall be learning a lot about the biosafety and biosecurity in the realm of dual-use research of concern, which will be discussed again by our research speaker, Dr. Elpidio Cesar Nadala Jr., a Balik Scientist from Diagnostics for the Real World Limited in the United States. But before I turn you over to our speaker, let me first give a recap of our session yesterday. We were able to get to know our scientist through his shared experiences in the handling of pathogens and the different biosafety levels. He tackled dual-use research of concern, or DURC, which are life sciences research that, based on current understanding, can be reasonably anticipated to provide knowledge, information, products, or technologies that could be directly misapplied to pose a significant threat with broad potential consequences to public health and safety. He also discussed IREs, or institutional review entities, and the processes involved in biosafety and biosecurity. He also briefly discussed the 15 select agents, which are pathogens of concern, which we as researchers should be careful in dealing with, as they can do great harm if not treated with utmost care and respect. There was also a discussion on the 7 categories of experimental effects, which is what we would observe if we deal with any pathogens in our labs, and highlight the need for strict measures of biosafety and biosecurity. We also talked about the potential for bioterrorism and the different classifications of bioterror agents and diseases, and how these agents can be contained. He also later outlined the duties and responsibilities of investigators and institutions in preparing IREs and evaluating DURCs, as well as risk mitigation strategies in order to help keep us researchers and the community we serve safe from potential harmful effects of the pathogens we study. For the next part of this webinar, let us all welcome again Dr. Nadala. A virtual round of applause for our speaker.
So thank you, Bernard. So now I'm going to share my screen. Let's see. I'm not seeing. Bear with me here. I'm trying to get my screen up. Okay, there we are. Good. So you see my screen now?
Yes, sir.
Okay, so I'll start. Welcome, everyone. This is the second part of my webinar on biosafety and biosecurity in the realm of dual-use research of concern. So yesterday we discussed biosecurity, and today I'm going to talk about biosafety. When working with biological agents, you remember this particular slide, but I'm going to go through it again. A laboratory facility must have risk control measures in place for the work to be safely conducted. And the two considerations are biosafety and biosecurity. So we've tackled issues on biosecurity yesterday, bioterror weapons, or organisms and toxins that can be used as weapons of mass destruction or in bioterrorism. So biosafety, and most of you have seen this symbol. This should be placed on a door, access to a lab with a certain level of biosafety. And these levels are 1, 2, 3, 4, depending on how much protection, how much measures are there to protect people from biological agents being worked on in the lab. Suppose you are a laboratory microbiologist working with a potentially harmful microbe. So this range from bacteria to viruses to fungi and more. So precautions must be taken in the laboratory to make sure you and others are not infected. So as this cartoon shows, we don't want this kind of accident to happen. This is supposed to be the Center for the Study of Viral Pathology, and you see a broken jar on the sidewalk. So that's the kind of accident we don't want. So where in the lab would you complete your work? These are the things that you have to consider. And what protective equipment and practices would you use? How would you contain the microbe to limit contamination or accidental infection? These are just a few of the questions that can be answered through an understanding of biosafety. So biosafety is the application of safety precautions that reduce a laboratorian's risk of exposure to a potentially infectious microbe and limit contamination of the work environment and ultimately the community. Okay, so you might be working on a viral isolate from bats that you got from Mount Makiling, and you go back to your lab working on it. You don't want it to contaminate yourself, to infect you, and then when you go home, infect other people. It also refers to containment principles, as we will discuss later, technologies and practices that are implemented to prevent unintentional exposure to biological agents or their inadvertent release. Laboratories' biosafety and biosecurity activities are fundamental to protecting the laboratory workforce and the wider community against unintentional exposures or releases of pathogenic agents, biological agents. So these activities are implemented using a risk assessment framework and through the development of a safety culture, which is needed to ensure a safe workplace where adequate measures are applied to minimize the likelihood and severity of any potential exposure to biologic agents. So the biosafety risk assessment framework consists of the following. We sort of discussed this kind of framework before, yesterday actually, in terms of biosecurity. So it's very, very similar, except that in biosecurity, you have the institutional review entity, while in biosafety, you have the institutional biosafety committee. And the first step, of course, as we said yesterday, is to gather information. So what biological agents will be handled and what are their pathogenic characteristics? What type of lab work and procedures will be conducted? What type of equipment will be used? What type of laboratory facility is available to use? And what level of competency will the personnel have that's going to handle these agents? What other factors exist that might affect laboratory operations? For example, legal, cultural, socioeconomic, or even public perception. For example, you work with animals and you have animal rights and stuff like that. So you need to gather information on the experiments and the biological agent that you're working on, so that the next step would be to evaluate the risks associated with that activity and agent. So risks would be, how could an exposure or release occur? And what is the likelihood of an exposure or release? And so on and so forth. So just to go and look at all the risks in the whole process, in the experimentation. Then, knowing the risks, you develop a risk control strategy. Okay? So what resources are available for risk control measures? Later on, you will see the resources that are required. And what risk control strategies are most applicable to the resources that you have? And are they sufficient to obtain and maintain those risk control measures? Okay. So once you have devised how you're gonna manage the risks that you have seen, then you go and select among these risk control measures, what are you going to implement? Okay, so which control measures are appropriate? And finally, once you have carried out the experiment and then along with it, the measures to contain the organism so you don't infect people, then you continually review these risks and the risk control measures. So in other words, as you carry out the experiment, as months or year, have there been any changes in activities or the biological agents that you're working with, or the personnel, or the equipment that you use, or the facilities? Are you still working in the same lab? So all these things impact on the risks that the new risks, and then you have to come up with new risk control measures. So that's the framework. Now, challenges that will influence how various parts of the risk assessment framework are conducted may include, so we go back to what are the risks? The level of organizational and financial resources available to manage the biological risks. That's always very important. Absence of a reliable electrical supply. So is power always available and reliable? If not, then you have to take that into account. And inadequate facility infrastructure. So do you have even enough space? Do you have double doors? Do you have a sealed room? Do you have air supply management where you have HEPA filters, or that the air supply in the room are all filtered so you don't release agents to the environment? And then, of course, severe weather. You have to take that into account. Is there going to be a typhoon number 3 or 4 that will knock off your infrastructure and and release your agent. Yeah, those are serious risks. And then, of course, understaffed laboratories. Are there people who are available even to secure the place or to clean up or whatnot? And then, are your personnel trained? So if your personnel are undertrained, that's also a challenge. So in order to weigh the risk and assess the risks, there is a risk assessment matrix. And this matrix consists of, on one side, the consequences of exposure or release. So if you're exposed to the agent or it's released to the environment, to the people, how serious or severe are the consequences? Is it fatal? And fatal 30% of the time or 1% of the time? So the severity of the infection, for example, or the disease. The other side of it is likelihood of exposure or release. Okay, so this has to do with, how much of it are you producing, for example. So if you're producing liters and liters of culture, the likelihood that it will be released or that it will contaminate you is higher. So those are weighed against each other. And so you go from very low risk, where the consequence of exposure is negligible and it's unlikely to happen, to the very high, where it's a fatal disease and you're growing a lot of it. Okay. Or you're working with a wild type that is not attenuated. So the thing is, you normally start with determining the initial risk, right? So the information you gathered at the first step of the framework that we showed earlier is used to establish how much risk the situation presents. And then you will establish an acceptable risk. So once you have initial risk determined and evaluated, then you're going to say, how much risk can I take? You don't have to take the lowest one. Sometimes a low risk or even a medium risk can be acceptable. So it's necessary to determine what is acceptable. So if it's not acceptable, then a risk control strategy will be required to reduce that initial risk and sustainably control it so that you don't have a release. So it's important to note that risk can never be completely eliminated unless the work is not performed at all. So don't do it at all, then you don't have any risk. Therefore, determining if the initial and or residual risks are acceptable or controllable or unacceptable is a very important part of the risk evaluation process. So once you have determined the risk, the initial risk, and you need to reduce it, what are the risks or strategies for reducing risk? First is elimination. What do you mean? Use an inactivated biological agent. So if you have to work with, let's say, SARS-CoV-2 or even HIV, use an inactivated one, a killed one, so then you don't have any risk because it's dead. Use a harmless surrogate. So a similar organism or agent, but it's harmless. It doesn't cause any disease at all. You can also go, another strategy would be reduction and substitution. Again, so you substitute with an attenuated or less infectious biological agent. It's not dead or totally harmless, but it's less infectious. So you can use that. Or you can reduce the volume or the amounts or titers of the organism you use. That will also reduce the risk of exposure. You can change the procedure for one that is less hazardous, such as do PCR rather than culturing. Okay, so the next one is isolation. Okay, so you want to eliminate or reduce the risk. So you isolate the biological agent. So for example, you put it in a sealed bottle or vial. Okay, so there's no risk of release. The other one is protection. If you really have to work with it and you can't keep it in a bottle, so you have to use engineering controls. What are these? These are like biological safety cabinets. And these are different classes too. You have class 1, class 2, and class 3. Where class 3 you have no contact at all. You have gloves going into the cabinet. Or class 2, very common. Use PPE, personal protective equipment, and everybody by now knows what these are. Vaccinate personnel. So people who's going to work on the agent, vaccinate them so that if they do get exposed, the consequence of the exposure is very limited, no severe consequence at all. And I experienced this when I worked with hepatitis B virus also, that I got vaccinated first before I was allowed to work with it. Compliance, have administrative controls and effective biosafety program management. So that's sort of like an overall way to reduce risk. And we're gonna talk more about this later on, where it comes from. So the next step would be, so you have your risk control measures or strategies actually. And so now you're gonna select and implement which of these risk control measures you're gonna use. And so it would depend on, again, the severity of the consequence of exposure and the likelihood of exposure. And most of the time, you only need to have these core requirements for risk management, and not really the maximum containment measures, which are like level 4 biosafety, where people are wearing these like astronauts in there with their own oxygen supply. You don't need to go there most of the time. So some examples for you so that you know what I'm talking about, because so far these are sort of like generalities. So we're gonna have examples of procedures in the lab and what the initial risk was for that procedure and what risk control measures you should take and what the residual risk is after you've taken the control measures. So first, for example, you're doing PCR analysis of sputum specimen from some patient, but it's inactivated. So the initial risk is very low. The likelihood of release is unlikely because there's nothing there to release. It's inactivated and negligible consequence. So your risk control measures are just the core requirements, which we will go through after this. What are these core requirements? Very basic biosafety considerations in a lab. So the residual risk is also very low. So this kind of activity, really, there's not much to be concerned about. But if you were doing a smear preparation and microscopy of the sputum specimen, that means you're not going to inactivate it. it's a small specimen. It's still unlikely that you're going to get exposed. But there's some moderate consequence in case you do get exposed. It might have some, you might get sick. You won't die, but you might get sick. So there's low initial risk. And again, just the core requirements or core risk control measures would suffice. But if you're doing culture on solid media, let's say for antibiotic testing, okay, the risk there is a little bit, is now medium, because you're actually growing the agent. In this case, bacteria, of course. You can't do this with virus. And then the likelihood is it's possible. You know, it's possible that you will get exposed and you are going to get sick if you get infected. So now it's still the core requirements, but maybe it's a little bit more. You'll have to heighten control measures. Okay, so meaning you may want to have some respiratory protective equipment, like maybe the face mask, right? And so from a medium initial risk, it becomes a lower residual risk because you're taking measures. Okay, and if you were to culture in small quantities, about 50 ml culture, so this is not on solid media, now you have liquid that you're going to be manipulating of the strain that might be antibiotic resistant. So now you're getting into a higher initial risk and likely exposure. And again, you can get sick. So again, you need some heightened control measures and probably using a biological safety cabinet to be able to mitigate the risk. Now, if you're going to culture large quantities for use in animal challenge study, for example, via aerosol, then the initial risk for you is high. You could possibly get infected and you might have more severe disease. Again, you need heightened control measures, for sure biological safety cabinet, and also respiratory protective equipment. And your residual risk is medium. Finally, if you had a biological agent that's globally eradicated, like smallpox, with studies ongoing with these procedures, then very high risk, and you need the maximum containment measures. And after you implement that, you still have some medium residual risk. For most labs, medium risk is acceptable. So once you have determined the risk and risk control measures, then you review them. You carry them out, and then you review them and assess and revise if necessary. And again, if there are new information, then you have to make some changes. So activities or events that affect the risk and will therefore trigger a risk reassessment include changes to biological agents, as I said before. I think we've gone through this, changes in personnel, procedures, new technology that you're using, if you relocated your lab and all that. So these are all part of that framework that we talked about earlier. And of course, you need periodic review. So what are these core requirements that I started talking about, okay, that you need to have in any lab? So it's a term used to describe a combination of risk control measures that are both the foundation for and an integral part of laboratory safety. Okay, these measures reflect international standards and best practice in biosafety that act as a set of minimum requirements and considerations that are necessary to work safely with biological agents, even where the associated risks are minimal. So if any of you are working in a lab, please pay attention because these are things that are very important for your own safety and the safety of people who work in your lab. So the first part of these core requirements is good microbiological practice and procedure. Okay, so that's GMPP, good microbiological practice and procedure. It's a term given to a set of standard operating practices, SOPs, standard operating procedures, or a code of practice that is applicable to all types of activities with biological agents. This includes both general behaviors, your general behavior in the lab, best working practice and technical procedures. Okay, so whether you are actually doing something, an experiment or not, you have to behave a certain way when you're in the lab. That should always be observed in a lab and conducted in a standardized way. So first is best practice. This describes behaviors that are essential to facilitate safe work practices and control biological risks. Number one, never store food or drink or personal items such as coats and bags in the laboratory. Activities such as eating, drinking, smoking, and applying cosmetics are only to be performed outside the lab. So don't put on your lipstick or your eyeshadow in the lab. Never put materials such as pens, pencils, or gum in your mouth while inside the lab, regardless of whether gloves are worn or not. Okay, a lot of people have this habit of putting pens in their mouth or pencils. Never do this in the lab. Wash your hands thoroughly, preferably with warm running water and soap after handling biological material and or animals before leaving the lab or when hands are known or believed to be contaminated. More best practice. Ensure open flames or heat sources are never placed near flammable supplies and are never left unattended. Some labs have burned down because of this. Ensure that cuts or broken skin are covered before entering the lab. And before entering the lab, ensure that there are adequate supplies of lab equipment and consumables, including reagents, PPE, and disinfectants, and that these items are suitable for the activity you're planning for the day. Ensure that supplies are stored safely and according to storage instructions. This is to reduce accidents and incidents such as spills, trips, or falls. You don't have stuff on the floor that people can trip on. Ensure proper labeling of all biological agents and chemicals and radioactive material. You shouldn't have tubes that don't have label, that looks like a culture, or any kind of liquid in a tube that is a chemical but has no label. Of course, radioactive material, that's very rare nowadays unless your lab still deals with it. Protect written documents from contamination using barriers such as plastic covers, particularly those that may need to be removed from the lab. So when you take it out and it's been contaminated, then you're releasing the biological agent. Ensure that the work is performed with care without hurrying. Don't rush it, and avoid working when you're fatigued, when you're tired. More best practice. Keep the work area tidy, clean, and free of non-essential objects and materials. Prohibit the use of earphones, which can distract personnel and prevent equipment or facility alarms from being heard. Cover or remove any jewelry that could tear your gloves easily, become contaminated, or become fomitase. Cleaning and decontamination of jewelry and spectacles should be considered if such items are worn regularly. Refrain from using portable electronic devices, your mobile phones, your tablets, laptops, flash drives, memory sticks, cameras, other portable devices, including those used for DNA-RNA sequencing when not specifically required for the lab procedure being performed. And keep portable electronic devices in areas where they cannot easily become contaminated or act as fomites that transmit infection. Okay, where close proximity of such devices to biological agents is unavoidable, ensure the devices are either protected by a physical barrier or decontaminated before leaving the lab. So those are best practices. Now we turn to technical procedures. Notice that best practices are just what everybody should be doing, whether they're doing anything or not in the lab. So technical procedures are a special subset of the good microbiological practice, which relate directly to controlling risks through safe conduct of laboratory techniques. There's a lot of techniques, but I'll just go through some of the common ones. Avoiding inhalation of biological agents. So use good techniques to minimize formation of aerosols and droplets. These things may not be visible to you when you're manipulating the specimens. So that means you refrain from forcibly expelling substances from pipette tips into liquids or over vigorous mixing and carelessly flipping open tubes. Where pipette tips are used for mixing, this must be done slowly and with care. Brief centrifuging or mixed tubes before opening can help move any liquid from the cap. So notice that when you do your vortex mixer, a lot of the liquid will splash to the cap. If you don't spin it down briefly and open it, then that liquid will go to your gloves or will be suspended in the air, whatever aerosols were generated by the mixing. Avoid introducing loops or similar instruments, you know, the wire loop that you use for bacterial work, directly into an open heat source flame, as this can cause spatter of infectious material. So where possible, use disposable transfer loops, which do not need to be re-sterilized. Or an enclosed electric micro-incinerator to sterilize metal transfer loops can also be effective. Those are these barrel-shaped micro-incinerators that heat up inside instead of an open flame. Okay, next technical procedure, avoiding ingestion of biological agents and contact with skin and eyes. They don't mean that you're gonna drink it or eat it, but you wear disposable gloves at all times when handling the specimens known or reasonably expected to contain biological agents. So disposable gloves must not be reused. Once you think you have contaminated it, remove it and put it in the biological trash. Avoid contact of gloved hands with the face. So that's how you're gonna have contact with your skin. Remove gloves aseptically after use and wash your hands. Shield or otherwise protect your mouth, eyes, and face during any operation where splashes may occur, such as during mixing or disinfectant solution. So this is where face shields are very, very important. Secure your hair to prevent contamination. Cover any broken skin with dressing and prohibit pipetting by mouth. Next is avoiding injection of biological agents. Again, you're not going to inject yourself intentionally, but don't use any glassware, because then if it breaks and you injure yourself, plasticware is preferable because they don't generate sharps. If required, use scissors with blunt or rounded ends so you don't poke yourself with their pointed end. If glassware must be used, check it on a regular basis for integrity. Discard it if it's cracked, chipped, or broken. Use ampule openers for safe handling of ampules. These are the glass ampules. Minimize the risk associated with the use of syringes or needles by using blunt syringe needles, alternative devices, or engineered sharp safety devices where possible. Never use syringes with needles as an alternative to pipetting devices. The needles are easily accidentally poked into your skin. Never recap, clip, or remove needles from disposable syringes. And dispose of any sharp materials in puncture-proof, puncture-resistant containers so they don't stick out and poke anybody. Okay. Preventing dispersal of biological agents. You discard specimens, cultures, for disposal in leak-proof containers with tops appropriately secured before disposal in dedicated biological waste, biohazard waste containers. Place waste containers, preferably unbreakable containers, at every workstation. Regularly empty containers and securely dispose of waste. Ensure all waste is properly labeled. Consider opening tubes with disinfectant soap pad or gauze because the cap, as I said, might have some contamination. Decontaminate work surfaces with a suitable disinfectant at the end of the work procedures, and if any materials are spilled. And when disinfectants are used, ensure that it's active against the agent that you're handling and is left in contact with the waste material for the appropriate time according to disinfectant being used. For example, I was working with poliovirus at some point when I was in graduate school, and I recognized that the only thing that can kill it, or the hepatitis A virus as well, was Clorox. If I use alcohol, it's not going to die. Instead, it's going to infect me. So you just be aware of how you disinfect and what you're trying to disinfect. Again, so personnel competence and training. Human error and poor technical skills can compromise the best safeguards that we've just talked about. Thus, competent and safety-conscious laboratory personnel who are well-informed on how to recognize and control laboratory risks are essential for the prevention of laboratory-associated infections and or other incidents. Okay, so general familiarization and awareness training of the personnel in terms of the layout of your lab, what are the equipment in there, what features does it have, do you have a sink, where is the sink, eye wash area, and they should be familiar with the laboratory codes of practice that we just enumerated. And then they should be also trained for the specific jobs that they are going to do. This depends on their job function. They should be involved. All personnel that are involved in handling of biological agents must be trained on good microbiological practice and procedure. And then, of course, there should be safety and security training. So awareness of hazards in the lab and their associated risks, safe working procedures, security measures so that, you know, not just anybody would just walk in your lab that don't work there, emergency preparedness and response. So if something happens, you should know what to do, or anybody in the lab would know what to do. So I might be able to have time to discuss this. Like, for example, if there's a spill of a biological material, what would you do? What would anybody in your lab do? Okay, so they should have that. Then facility design. This is where this is more on management, how your lab facility is designed. It should have features that I'm going to list now as core requirements for biosafety of your lab in handling biological agents. There should be enough space for safe conduct of your work, laboratory work. It shouldn't be so tight that you're, hitting each other, or you can't even clean the place anymore because everything is everywhere and you have no floor space. Designated hand washing basins operated by hands-free mechanism must be provided in each laboratory room and preferably close to the exit door. Just before you leave, you should wash your hands. The laboratory must be a restricted access area. Laboratory entrance doors should have vision panels to avoid accidents. When you open it, you know who's on the other side. Appropriate fire ratings and preferably be self-closing. Doors must be appropriately labeled with the International Biohazard Warning symbols where biohazardous materials are handled and stored. So laboratory walls, floors, and furniture must be smooth, easy to clean, impermeable to liquids. So even chairs should not be permeable to liquids. Resistant to chemical disinfectants normally used in the lab. Bench tops must be impervious to water and resistant to disinfectants, acids, alkalis, solvents, and moderate heat. Lab furniture must be fit for purpose. Open spaces between and under benches, cabinets, equipment must be accessible for cleaning. And laboratory lighting must be adequate for all activities. And laboratory ventilation, where provided, should ensure airflows do not compromise safe working. So the airflow speeds and directions, turbulent airflows should be avoided because those will tend to spread whatever aerosols they are generating. Laboratory storage space must be adequate to hold supplies for immediate use to prevent clutter. Okay, so a lot more facility design requirements. These are all core requirements. So eating and drinking, we've already talked about. There should be first aid facilities. And then, of course, methods for decontaminating your waste have to be provided, whether it's disinfectants, autoclaves, and management of waste must be considered in the design. So, and also you have fire, electrical emergencies, and reliable and adequate electricity supply and lighting to permit safe exit. Emergency situations must be considered in the design as indicated in local risk assessment and should include the geographical meteorological context of your facility. Okay, so when your lab receives a specimen, there are also safe handling procedures, and the people who receive this should be trained. Okay, so unpacking and adapting precautions. When you see something broken, the person should know what to do. Somebody yesterday asked me about how to ship or transport these infectious substances. There are two basic categories of biological agents. One that can cause permanent disability or a fatal or life-threatening disease. That's category A. The category B would be biological agents that will cause infection and in some humans, but not really fatal, or in animals, but are not life-threatening. So those are two categories of biological agents, and there are United Nations identifiers for this that you have to put in the label for your shipment, or, when you ship it or you transport it. So, and each of these have UN identifiers have some requirement on what they might be, like whether it affects humans or it affects only animals or it's just a solid waste. And so there are documentation requirements and packaging requirements. Most of the time you will want to triple pack it. And that's required for shipment. And an example of a triple packaging material for category A, for example, would be something like this, where you have your agent in a sealed leak-proof primary container, and then you have an absorbent pad in case it leaks, and then you have a sealed secondary packaging, and then finally you have the third outer packaging. Normally you would have some dry ice here or some ice pack to preserve or keep temperature down. So again, also specimen storage is very important in biosafety. You should have the right containers, of course, and made of plastic if possible. And then, of course, you have to label it properly so people know what it is. And also, there are considerations about decontamination and waste management, as I mentioned earlier. So several ways. You have chemical disinfection, and you have to choose the right disinfectant that it's appropriate for your biological agent. And what are you going to apply it to? Is it a surface or is it in liquid form? And how long does it have to work and all that? So also autoclaving is an option. And when you use it correctly, it's very effective and reliable. It can kill and inactivate biological agents. So they're usually used at high temperature, and that's achieved through pressure. So it's a pressurized, it's kind of a pressure cooker. So it looks something like this. You put your bag in there, and then steam goes in, cold air goes out, and then pressure. And you expose that for at least like 15 minutes at a certain high temperature. Incineration is another method that's used, but of course there are approvals from local health authorities and air pollution considerations for that. Personal protective equipment, everybody's familiar. Lab coats, footwear, closed shoes, gloves, normally latex, but some people are allergic, so there are alternatives. Eye protection, face shield is the best. Respiratory protection, such as a face mask. And again, also lab equipment. So one has to use these equipment safely. And so training, of course, is important to reduce risks. And so the maintenance of the equipment. So for specialized lab equipment, for example, pipettes. So we already talked about not generating aerosols when you use pipettes, so you don't blow on it. Centrifuges also have to be operated and serviced according to manufacturer's instructions. I've known rotors in these centrifuges flying up and hitting the roof because people didn't balance them properly. Refrigerators, of course, they have to be spark-proof. And if you're going to store flammable solutions in there, you don't want it to go up in smoke. And of course, emergency incident response, there has to be SOPs for this, standard operating procedure. What if there's a fire, or what if there's a flood and all that? Or what if somebody suddenly keels over with a heart attack or something? How are you going to take care of that? And then, of course, occupational health, meaning, vaccination again, for example. And people have to have safe working environment to work in a lab. And biological spill response. So this is what I was talking about earlier. If a spill occurs where there is a high risk, initial risk of formation of aerosols or high volume of spill of the high pathogenic biological agent, so you should have, personnel must immediately leave the area. Okay, leave the area. Don't stand around and stare at the spill. Exposed persons should be referred immediately for medical evaluation. The room containing the spill should not be entered for some time so that the aerosols can be removed or settle. And then if there's an exhaust system, then at least those aerosols can be caught in the filtration. And you have to have signs about what happened, and then biosafety officer is informed, and so. Now, I want to go through the biosafety levels because this is very important. We're done with the core requirements, okay? So now we go through the biosafety levels. These are the additional protection that you can have depending on the agent you're working on. So biosafety level has its own containment controls that control the risk of release or contamination. And these have to do with laboratory practice, so how you're gonna carry out your work in each of these containment levels, what safety equipment you're using, and how the facility is constructed. Okay, so levels of containment precautions required to isolate dangerous biological agents. You have biological safety level 4 on top, where you're working with exotic agents, you know, the meanest, nastiest bugs. And then you have BSL 3, where you work with bugs that are more easily transmittable, and they're also exotic microbes, potentially lethal. So this would include SARS-CoV-2 if you're growing it in cell culture, for example, or TB, high concentrations of it, and of course, the highly pathogenic avian influenza or plague. Then below that, BSL-2, which most microbes that I know that can cause disease but are not necessarily lethal or aerosolized easily are in this level. And BSL-1, of course, is microbes that don't really affect you even if they infect you, like E. coli, the ordinary one, not the 0157. So every microbiology lab, regardless of biosafety level, follows the standard microbiological practices or the core requirements that we went through. So a biological safety level 1 facility, okay, the microbes there are not known to consistently cause disease in healthy adults and present minimal potential hazard to laboratories and the environment. So these are the microorganisms like E. coli that you work in your microbiology lab, okay, if you've taken this in college. So you have a door, and you should also have a sign if you're working on microorganisms in here, but you have controlled access essentially, and you have a hand washing sink, you have a sharps bin or container, you have your PPE, your closed shoes and gloves and lab coat and your eyewear or protective equipment for your eyes. And then you have a bench where you can do your work. Of course, optionally, if you need to decontaminate, you can have, but not required, an autoclave. Okay. The next level is biosafety level 2. Again, you have controlled access, you have the sink, but now you have this number 4, this physical containment device. And this looks like a class 2 cabinet, okay? So a class 2 cabinet, the air there is circulated and filtered and is expelled out There is essentially an air curtain here that if aerosols are released in there, you don't inhale it. Of course, you have all the other things, but normally an autoclave is now required. So that's biological safety level 2. Biological safety level 3 now has even more stuff. So you see, you might have a powered air purifying respirator. You should have double doors. Okay, so you have a door out there and a door in here. Optionally, you can even have a shower here in case you need to decontaminate yourself. But the double door is required for BSL 3. And this room should be airtight. Okay, you still have the same ones as BSL 2, but this should be airtight, and you have an exhaust system with HEPA filtration. Besides the filtration in the cabinet, the whole room will be HEPA filtered. And all the effluent from your hand washing, that has to be decontaminated too. Okay, so this one is like if you're working on HIV or SARS-CoV-2. And the final biosafety level is biosafety level 4. So this is what I said, you look like an astronaut here. You have your own air supply. Even if aerosols are released in this room, you're protected. So again, you have, these ones now are required HEPA filtration and decontamination. And you have also a chemical shower before you get out. So you really have to shower here because you have to decontaminate your suit. Okay, so this is my final slide. A review of recent laboratory-associated infections showed that most were caused by human factors rather than malfunctions in engineering controls. And factors that have led to potential and confirmed exposures to biological agents include an absence or improper use of PPE. Okay, when you wear your face shield, your nose shouldn't be out. Okay, so if you are at all, if you wear your face shield, don't put it up on your head. Wear it properly. Inadequate or ignored risk assessments. So there are risk assessments, and people are working in the lab have to be informed and educated of these before they even start. So if they ignore that, then you have problems. Lack of SOPs. People don't know what to do when they get a spill or somehow prick themselves or whatever. And also even just plain SOPs in terms of when you leave the lab, this is what you have to do. Those have to be followed. Needle stick injuries and or insufficiently trained personnel. We already mentioned about training people for the job they're gonna do. So it can be argued, therefore, that the best designed and most well-engineered lab is only as good as its least competent worker. So training is very important. That's it. So I'm open for questions.
Okay, thank you very much for that very informative presentation, Dr. Nadala. So that ends our learning session for the biosafety and security in the realm of dual-use research of concern. At this point, we are open to your questions, and I know that our speaker will do his best to answer the questions. So for your questions, please key in your questions in our chat box in this Zoom meeting room. Our audiences from our Facebook and YouTube live stream may also type in their questions in the comment section so that our moderators can pick them up and be answered by Dr. Nadala. So we have quite a few number of questions already. Some of them were from yesterday, like Fernand Rascal asks, in connection with the bioterrorism, is it possible that the new variants arising now are also bioengineered? How fast can a certain scientist identify if a certain virus is man or even synthetically made?
Yeah, it's easy. You just look at the genomic sequence. All viruses are made from the genome of that virus, and it's easy to tell if it's engineered a genome rather than a naturally evolved genome. SARS-CoV-2, although it's highly infectious or easily transmitted, is not really that deadly. If you look at the death rates, 1%, 2%, 3% at the most, that's not like smallpox where it can kill you 30% of the time or even deadlier bugs. So it's not an ideal bioterrorism agent. Out of 100 of your opponents or people you're trying to kill, only 2 or 3 will die. So really so I wouldn't consider that as a good bioterrorism.
Okay, so you don't think SARS-CoV-2 was bioengineered?
No, I don't think so. I think it might have arisen from a lab accident, a biosafety issue. We know that any biosafety lapses or infection, it might be human error. You might have the best facility, but
okay, our next question is from Samuel Waiba. Nowadays, we are having superbug and mutated virus due to overuse and improper use of antibiotics and antibodies. In this COVID-19 pandemic, people are also overusing hand sanitizer. Do you think it is also promoting to the rapid mutation and becoming resistant to alcohol?
no. The way alcohol works, not like antibiotics. It's the bugs, I don't think would develop resistance just like that. They would develop, I mean, there are bugs that are okay with high alcohol levels, but I don't think it's one thing that it's not the same as our problem with the antibiotics. I think our problem with antibiotics is a very, very big problem indeed. And we are actively looking for alternatives, including phage therapy, bacteriophages. But no, I'm not concerned about alcohol resistance.
Okay. Jasper Perez asks, what would be a sound rationale for making an agent more infectious, noting in the first place that it is already highly pathogenic?
Yeah, so what you want to do there is when you try to make it more infectious, meaning easily transmissible, for example, you are trying to anticipate what it can evolve into. We're talking about, for example, the avian influenza virus. The question is whether can it easily go to or infect humans from birds, and some experiments that might anticipate that might try to change, for example, the hemagglutinin and neuraminidase proteins so that it can bind to our cells. So that's making it more infectious. But what you're trying to do also is to see whether it can do that and then anticipate it so that later on, when it does do that, you know what to do. It's kind of how you would counter it. And that's why a lot of governments are still retaining these, like smallpox or something, because they want to be able to counter later on, whether it's making a vaccine or figuring out how to block the agent with whether it's antibodies or therapy drugs.
Oh, okay. Very nice. A bunch of people ask, where will the disposed biohazard waste or equipment go? Can it be reused or recycled?
So when it's biohazard equipment, normally you disinfect with either with chemically. You don't really want to autoclave your equipment. And so normally it's chemical disinfection. Now the sharps and other medical waste, they're normally incinerated. And the cultures you have in your lab, including contaminated plasticware, those are autoclaved. And when they have been autoclaved, they can be thrown in the trash, normal municipal trash. But most of the medical waste are incinerated from hospitals and also labs, those that can't be autoclaved.
Okay. Ben Richard Lafuente from Colegio ng Subic asks, had your team experienced exposing in some agents while performing in the laboratory? How do you react or made an action to resolve the problem?
Can you repeat the?
So, has your team experienced exposing the agents while? I guess what they're asking is, has an agent escaped from your laboratory, and how did you react, or how did you acted on the problem?
Okay, so I worked with hepatitis A virus initially, and everybody in the lab were afraid because it's hard to inactivate. So I sort of had my own lab. Didn't happen. It didn't infect me or anybody else there. No, I can't remember when we were working with HIV. Nobody came down with HIV. You just have to follow the protocols, and as I said, you need to learn how to work with these agents. I was working also with E. coli 157 and Salmonella, and my boss was very, very nervous because I might get infected when I was doing microscopy and all that, but it never did happen. I heard about one of our employees who got sick and seemed to have 0157, but basically she just was treated because it's just E. coli, and she recovered. She was working in the food lab where they screen food samples for 157. So it happens, but it depends on the agent. I have never worked with really highly fatal agents in a BSL-4 level, so I never really experienced such a devastating outcome. And we have, as far as I can tell, never released an agent to the outside and infect more people.
Okay, that's good to hear. What are the appropriate vaccines that should be regularly provided for lab workers handling biological agents? So this is asked by FNRI's Christine Eden Cortez Sevilla.
Only if there are vaccines available. Of course, hepatitis B, if you work with that, there's an available vaccine, so they will require you to have antibodies. If not, then you need vaccination. And HIV, there is no vaccine, so really you can't be vaccinated. The others, HCV now has a vaccine. But when I was working with Hep A, there was no vaccine. So basically the answer to that question is, if you're working with an agent that has a vaccine available, then you need to be vaccinated to protect you.
Okay, another question from Willie Sempita Jr. from Letran. Are there any existing regulations or laws pertaining specifically to biosafety? Is there a need to have a certified or licensed biosafety officer for biosafety research laboratories?
Yes, absolutely. all research labs should have a biosafety, institutional biosafety committee. The institution itself, not just the lab. Yeah, if you're just a lab in, let's say, in an institute, then you don't have to have your own, but definitely your institute will have a biosafety committee and assigned biosafety officers, whether it's chemical or biological. When I worked in a lab in Seattle, we had a biosafety committee who take care of that. And but if you work in your lab yourself, I mean, in a smaller lab, like headed by one professor, then the professor will need to make sure you guys are trained and also educated on your biosafety procedures.
Okay, we have time for one last question. A bunch of people ask, is the current PH setup and capability, do we have BSL-4 labs? And is there a need to build a level 4 biosafety lab here in the Philippines? Can the Philippines support the maintenance of a level 4 biosafety lab? And what does the virology lab will be on those level 4 biosafety classification? I think it's nice. It's nice to say right now that the VIP, the one that we are establishing right now, it will contain a biosafety level 4 lab. But are you aware of any other level 4 labs here in the Philippines, Dr. Nadala?
No, I'm not aware. And you only need the level 4 lab for a few select agents. And so unless you're planning to work with those agents, then there is no need for it.
Yes, but for all of those who are curious, the VIP, the Virology Institute of the Philippines, will establish what I think the first, unless someone has beaten us to it, the first VIP level 4 laboratory here in the Philippines. So thank you for that. Thank you for all your questions. In the interest of time, we'll be ending the Q&A session now. For those remaining questions, wag po tayo mag-alala because we'll be sending you the answers through your email. So, and now to present the certificate of appreciation to our speaker. Unfortunately, our director, Dr. Annabel Vibriones, is not around. So we might, okay, we're just going to present it right now. The Industrial Technology Development Institute presents this certificate of appreciation to Dr. Elpidio Cesar Nadala Jr., Balik Scientist from the Diagnostics for Real World Limited USA, for sharing his expertise as a resource person for the webinar entitled Biosafety and Biosecurity in the Realm of Dual-Use Research of Concern, as part of the establishment of the Virology and Vaccine Institute of the Philippines program of the Department of Science and Technology, held online on July 29 to 30 via Zoom. Given the 30th day of July 2021, signed by Dr. Annabel V. Briones, the Director of ITDI DOST. And now, for our closing remarks, may I call upon the Chief of the Environment and Biotechnology Division of ITDI DOST, Engineer Reynaldo Esguerra.
Thank you, Bernard. Good afternoon, Dr. Nadala. It's our second time to meet each other. So again, thank you for being part of our Balik Scientist program. And I'm sure that it had been another productive two-day lecture for you. And as I was listening towards the last part of the lecture, practically on biosafety and biosecurity, I suppose when we eventually transfer the VIP to Capas Tarlac, Dr. Cesar Nadala would be of great help when we try to establish our ISO 35001 or our biorisk management for laboratories. And well, just for during the last week's session where Dr. Lourdes Nadala was our speaker, I mentioned that the House of Representatives during that time said that Virology and Vaccine Institute of the Philippines was on top of their agenda. And true enough, only this week, it had been approved by the House of Representatives. So now we're just waiting for next week's session at the Senate. And hopefully they just adopt the version of the House of Representatives so that there won't be any problem in the consolidation of these bills towards the approval into an act establishing the Virology Institute of the Philippines. And I think we will be having the courtesy call of all our 7 Balik Scientists with our secretary come, I think that will be in 2 weeks' time. So I'm sure we'll see Doctors Nadala, Cesar, and Lourdes together. Our group would be seeing them together. Again, I'd like to thank the participants who, I think we have more than 280 participants for today. And also, of course, our partner divisions in doing this, our technological services and planning and management information system divisions. Of course, our VIP team led by Dr. Annabelle and our colleagues from CED, and of course, our division, Environment and Biotechnology division, especially, of course, special mention si Bernard, who moderated yesterday and today's session. So again, we hope that the good news for the Virology and Vaccine Institute of the Philippines continue to proceed towards its realization into a full Republic Act. So maraming salamat po sa lahat. Dr. Cesar Nadala, as usual, halong po, take care. Kami po dito, next week, we're still again, because it's general community quarantine, but we would be downgraded again to ECQ starting August 6 to August 20. So,
yeah,
thank you. But the good news is at our division alone, we're more than 80% vaccinated, full vaccine na. Although we still have to look at the studies on the efficacy or how long do we need our next booster shot for the vaccine we receive. So maraming salamat po ulit at kumusta lang po kay Dr. Lourdes.
Yeah.
Good afternoon.
Thank you.
Okay, thank you, thank you, Engineer Esguerra. And again, also, thank you to all of those who joined our learning session for today here on Zoom, on Facebook, and on YouTube. Please answer this evaluation form flashed on your screens right now to secure a copy of your certificates. Again, this has been Bernard Gutierrez of the DOST ITDI. Do like and follow lamang po ang Environment and Biotechnology Division Facebook page for announcements regarding future webinars. Magandang araw, and again, thank you.
Thank you.
Thank you.
Bye.
Hudyat na ng pagpasok, paglilingkod na walang kapalit, sa bayan ng aming hatid. Tara na, kaibigan, huwag kang magpaiwan. Gamitin ang dunong bansa'y susulong. Ating abutin ang pangarap ni Juan sa pamamagitan ng agham. Ang kaunlaran ay makakamtan kung lahat magtutulungan. Tara na, sama hamon ay haharapin, mahirap man ay kakayanin. Sa pinagsamang lakas at galing, tagumpay ay mararating. Tara na kaibigan, huwag kang magpaiwan. Gamitin ang dunong bansa'y susulong. Ating abutin ang pangarap iwan, sa pamamagitan ng agham. Ang kaunlaran ay makakamtan, kung lahat magtutulungan. Tara na, sama-sama, itaguyod ang siyensya. Maayos na bukas para sa Pilipinas. Ating abutin ang pangarap iwan, sa pamamagitan ng agham. Ang kaunlaran ay makakamtan, kung lahat magtutulungan. Tara na, sama-sama,
Recording
itaguyod
stopped.
ang siyensya. Maayos na bukas para sa Pilipinas.
Ang pangarap ko ay maging piloto.
Pangarap kong magkaroon ng chief alternative for personal hygiene.
Pangarap kong magkaroon ng mabilis at murang transportasyon para sa lahat.
Pangarap kong masagot ang malnutrition.
Pangarap ko pong magkaroon ng effective communication means for emergency.
Pangarap kong ma-maximize yung renewable energy source and to reduce the carbon dioxide emission.
Pangarap ko pong maging scientist.
Ngayon na o simulan na, humanda sabay-sabay aakyat. Hawak kamay tayo'y aangat, lipad. Lipad. Ating abutin ang pangarap iwan, sa pamamagitan ng agham. Ang kaunlaran ay makakamtan, kung lahat magtutulungan. Tara na, sama-sama, itaguyod ang siyensya. Maayos na bukas para sa Pilipinas. Ating abutin ang pangarap iwan, sa pamamagitan ng agham. Ang kaunlaran ay makakamtan, kung lahat magtutulungan. Tara na, sama-sama, itaguyod ang siyensya. Maayos na bukas para sa Pilipinas. Maayos na bukas para sa Pilipinas. Maayos na bukas ating iparanas sa bayang Pilipinas. Ating abutin ang pangarap iwan,